In this video, we will discuss conjugation and pi systems using molecular orbital theory. The learning goals for today are to be able to identify a conjugated pi system, to count the number of pi electrons in a pi system, draw the pi molecular orbitals for a pi system, and identify the frontier molecular orbitals for a conjugated pi system. Then describe how light affects the electrons in a pi system. Wow, which of these words are coming up again and again? Well, pi system, which I've already highlighted. Whoa, that's in every single goal. So what is a pi system? The only weird part of that is the system part, right? What's another word coming up again and again and again? Yes, conjugated, conjugated, and then we see molecular orbitals, and then we have light affecting electrons. We know that this will be explained by molecular orbital theory based on our last lesson. So we have conjugation, pi system. We know we're going to be using molecular orbital theory. There's questions about where electrons are. We know those are in molecular orbitals. Let's go ahead and define this word conjugated or conjugation. So conjugation just means connected. Let's keep that in mind as we get started. We'll get started with a question. Why are tomatoes red? All right, many of you know the answer to this. Tomatoes contain lycopene, which is a naturally occurring pigment responsible for their red color. Lycopene is an organic compound. We would describe it as a hydrocarbon. And frankly, it looks pretty boring. Don't you think it looks boring? There's just a bunch of alkenes. Whoa, lots of alkenes, but that's the only functional group. Let's call it a polyene. Many alkenes. So it looks super duper boring, but it's red. And that's a bit weird because most organic compounds are typically colorless. So you'll encounter some white powders. Pretty boring. But lycopene, not boring. It is red, and tomatoes contain it, and thus tomatoes are red. Cool. How can we explain that? Why is lycopene red if most organic compounds are just white powders? All right, well, if you think you know, write it down. Hopefully we can get to the bottom of this soon. But if alkenes are the only functional group, it probably has something to do with alkenes. Now, there are a lot of alkenes in lycopene. So just like for retinal, we used a simpler model. We used ethylene. For lycopene, since it's a polyene with many alkenes, let's use another polyene. Let's use 1,3-butadiene. As you recall from Organic Chemistry 1, but means 4 carbons. Ene means alkene. Di refers to the fact that there are 2 alkenes, 2 double bonds in this molecule. And finally, the 1,3 tells us the placement of the 2 double bonds. With that fun nomenclature review aside, I would very much like for you to draw a molecular orbital energy diagram for 1,3-butadiene. You should pause and do that now. If you do have a study partner that you can message, you can compare your answers. That would be wonderful. So let's pause. It really is important to today's lesson that you do humor me, pause, and draw the energy diagram for this molecule. So do that. And then before we move on, I just realized that I sort of goofed up a bit. So I learned organic chemistry multiple decades ago. And when I did, we would have named this molecule 1,3-butadiene. But since then, the rules for how to name alkenes have changed a bit. And now the numbers that describe where those 2 alkenes are located actually go just before the ene. So there's no confusion about what the 1,3 are referring to. They refer to the locations of the double bonds. So sorry about that. I'm sure that I have named other compounds this way in this lesson and on these slides, so I apologize, but 1,3-butadiene, buto-1,3-diene, we all know what we mean, hopefully. All right, so you have your molecular orbital diagram written down. You are ready to move on because we are going to revisit this MO diagram later. For now, though, we want to look at a few more examples that show that molecules that have adjacent alkenes, like butyl-1,3-diene, and like our example of the day, lycopene. Lycopene has a bunch of adjacent alkenes, right? Molecules that have adjacent alkenes show some unusual or unexpected reactivity. So let's look at a few more examples of that. Lycopene is red. That was unexpected when most organic compounds are white. And here is another clue that there is something going on. Cyclohexa-1,4-diene will undergo rapid isomerization to cyclohexa-1,3-diene in the presence of trace acid. It doesn't really matter what this trace acid is, what its chemical identity is, but for our purposes today, we can just imagine that it's hydrochloric acid. Cyclohexa-1,4-diene and cyclohexa-1,3-diene are constitutional isomers of one another. They differ in the location of the double bonds, which means that they differ in how the atoms are bonded or connected to one another. But they have the same exact molecular formulas, which altogether makes them constitutional isomers. If cyclohexa-1,4-diene rapidly isomerizes to the 1,3-diene, we can make a conclusion right away. So the second bullet point here says, what conclusion can you draw from this observation? Let's do that first. The conclusion that we can draw is that cyclohexa-1,3-diene is the lower energy constitutional isomer. Excellent, we can draw that conclusion, but can we explain it? Why is the 1,3-diene the lower energy isomer? If we take a look at the alkenes, in both cyclohexa-1,4-diene and in cyclohexa-1,3-diene, it just looks like there's two disubstituted alkenes. Think about what we know about alkene stability. We have used two main trends to evaluate alkene stability. First, more substituted alkenes are more stable than less substituted alkenes. For example, this tetrasubstituted alkene is lower energy, more stable than this trisubstituted isomer, which would be lower energy or more stable than this disubstituted isomer. So substitution pattern, more substituted is more stable than less substituted. We have also learned that trans alkenes are more stable than their cis isomers, because in the cis isomers, there can be a steric effect where these two alkyl groups are clashing in space, since all four atoms are coplanar. Unfortunately, neither of these trends can explain the difference in energy between cyclohexa-1,4-diene and its 1,3 isomer. So although we can draw the conclusion that the 1,3 isomer is lower energy, we're unable to explain why. Who thinks it might have to do with one of the highlighted words on this slide? All right, stay tuned. Although our focus will be on why the 1,3 isomer is lower energy than the 1,4 isomer, I do want to take a brief time out to provide a complete curved arrow mechanism for this transformation. Here's the cleaned up slide. Go ahead and give it a shot before I work through it with you. Last chance. Whenever we're problem solving, we write down the functional groups and we ask every molecule, what are you and how do you usually react? In the case of hydrochloric acid, it's a strong acid, and so it probably starts by protonating something. Looking at the dienes, we know that dienes will probably behave like alkenes and could undergo electrophilic addition reactions. Recall that electrophilic addition reactions occur when some electrophile accepts the electrons in the pi-cc orbital. Before we start the mechanism, let's try one more technique, which is to identify what bonds are made and broken from the starting materials to the products. We can see that we can see that a carbon-hydrogen bond between carbon 3 and hydrogen is broken, and that a carbon-hydrogen bond will be made between carbon 5 and hydrogen. Keeping that in mind, that this bond is made, what should hydrochloric acid protonate? Yes, perhaps carbon 5. So in an electrophile addition, elementary step, where the electrophile is the proton, the pi-cc electrons react with sigma star HCl, protonating carbon 5 and generating a carbocation at carbon 4. Because we have evaluated what bonds are made and broken from the starting material to the product of this isomerization, we know what to do next without really giving it much thought. The conjugate base of chloride could deprotonate here. These electrons and the carbon-hydrogen bond will now make this pi bond. And then the product has been generated and the acid catalyst regenerated. And although this would be a perfectly acceptable answer, most likely this cation actually undergoes rearrangement before it can react with the conjugate base chloride. What? Why? How? Let's give it a shot. So here's that cation, and this cation represents one of the patterns for when we should look out for carbocation rearrangement. The cation is adjacent to a carbon that is adjacent to a double bond. Oh my gosh. The cation is adjacent to a carbon that itself is adjacent to a double bond. So if a hydride shift occurs, a more stable cation is formed. More stable? What are you talking about? This is a secondary cation, and so is this one. Yes, well, this new one can be described by two resonance structures. The one that we have drawn and this resonance structure, showing that the charge and the electrons are delocalized, which makes this cation much lower energy than the one that was initially formed. Now, of course, the end result is the same. Chloride deprotonates either resonance structure and forms the diene that is observed. So you might say, well, who cares? The final result's the same. Who cares? How do you know that this even happens? Well, people study these things and there's pretty strong evidence, but let's not worry so much about that. You're right. It doesn't ultimately matter, but there must be some reason why I'm pointing it out. And let me just show you one thing here. So this definitely is a more stable cation, and we might even say that this empty p orbital is connected to the pi bond. Thus, the species is described by two resonance structures. Connected. Seems like I heard that word before. All right, wonderful. We have come up with the mechanism that explains how the 1,4 diene is converted to the 1,3 diene, but we have not yet figured out why the 1,3 diene is lower energy. So let's keep investigating. Let's look for some more clues. Why are these systems of adjacent alkenes so special? Are they even special? Well, here's clue number 2. We can compare the bond lengths in buta 1,4 diene to the bond lengths in butane. Why would we do that? Well, because I know what clues to look for. Also because the carbon 2,3 bonds we might expect to be pretty similar in these two molecules. They're both drawn as single bonds. However, if we take a closer inspection, and we either model these molecules with quantum mechanics or measure the bond lengths in some other way, we would find that the carbon 2,3 bond lengths are not the same for these two molecules. In fact, the carbon-carbon single bond between carbons 2 and 3 is quite significantly shorter for buta 1,4 diene than it is for butane. How can we explain this? Please write down an answer because you're all equipped with a possible explanation from previous classes. Here's an answer I've heard before from students, and it is a perfectly reasonable answer based on what you currently know about bonding. Carbons 2 and 3 and butyl-1,4-diene are sp2 hybridized, while carbons 2 and 3 and butane are sp3 hybridized. Thus, the carbon-carbon bond between C2 and C3 and butyl-1,4-diene is between two sp2 orbitals, whereas the carbon-carbon bond in butane between C2 and C3 is between sp3 orbitals. We may propose that because sp2 orbitals have more s character than sp3 orbitals, the sigma bond made between these two sp2 hybridized orbitals is shorter and stronger. If you came up with that explanation, good try, but we'll see. It's not quite the best explanation. More clues. Everyone loves heats of hydrogenations, right? To quickly remind you what a heat of hydrogenation is, an alkene can be treated with hydrogen gas in the presence of some catalyst. This adds an equivalent of H2 across the two carbons of the alkene. And some heat is released. This is an exothermic reaction. How can we understand that? Well, these two sigma CH bonds are being formed in the product, and those bonds are stronger than the pi CC and the sigma HH bonds that are broken in the process. The amount of heat released in this process informs us about the strength of the pi bond. So let's look at some molecules that are more complicated than ethylene. Here's our model for today of a molecule with adjacent pi bonds. This is that butyl-1,3-diene. When butyl-1,3-diene is fully hydrogenated, adding two equivalents of hydrogen across each of the double bonds in butyl-1,3-diene, 239 kilojoules of energy are released. We can compare that to when two equivalents of simply butyl-1-ene are hydrogenated. This total process releases 254 kilojoules of energy. Why are we comparing two molecules of but1-ene to the butyl-1,3-diene? Well, that's because there are two alkenes reacting in butyl-1-diene. And so to make a comparison, we need to hydrogenate two alkenes and but1-ene, but that requires two molecules. Okay, what is the point? Well, these numbers are different, right? The heats of hydrogenation are different for butyl-1,3-diene versus two molecules of but1-ene. And we don't necessarily expect them to be different, right? Hydrogenation of two alkenes should just be hydrogenation of two alkenes, but clearly that's not the case. So what we can conclude from this data is that two adjacent pi bonds have a different energy than two isolated by themselves pi bonds. Two adjacent pi bonds have a different energy than two isolated pi bonds. Well, you know what? We already have evidence of that. We saw that in clue number 1. Two adjacent pi bonds were lower energy than two isolated pi bonds. All this evidence is showing us that two adjacent pi bonds are lower energy than two isolated pi bonds. I think it's time to figure out why. So now it's time to stop, and I want you to pull out that molecular orbital diagram that I am sure that you completed when I asked you to quite a while ago for butyl-1,3-diene. And if you did not attempt to construct that molecular orbital diagram at that time, let's go ahead and do it now. Let's see if we can explain these observations. And let's list what these observations are with the diagram. Let's first list the observations. So adjacent pi bonds are lower energy than molecules with isolated pi bonds. We saw that in the isomerization example and in the heat of hydrogenation example. Because less heat was released when the two adjacent pi bonds reacted versus two isolated pi bonds. That suggests that this system was already lower energy than the two isolated pi bonds. Let's be sure we have that. Less heat was released in this hydrogenation because the starting material with the two adjacent pi bonds was lower energy. It started out at a lower energy spot. Okay, the two adjacent pi bonds, lower energy than two isolated pi bonds. That's why it's down here and these molecules are up here. So that's our first piece of evidence. And then our second observation or piece of evidence that adjacent pi bonds are different than isolated pi bonds was this bond length issue, that this carbon 2,3 bond length is shorter than a typical single bond. Recall this comparison that we made on this slide. So we're going to use molecular orbital theory to explain these observations. Well, we're not together in the classroom, so frankly, I do not know what you have drawn on your molecular orbital diagram. However, I suspect that many of you who attempted this exercise represented butyl-1,3-diene as two degenerate or isolated pi systems. But we have just discovered that this is probably not the case. That's okay. If you came up with this, I am extremely happy, but it is time to revise. Let's go ahead and do that together. 1,3-butadiene is clearly not just two separate alkenes. In fact, it's more stable than two regular isolated alkenes. In fact, if we look at the heats of hydrogenation data, it is about 15 kilojoules per mole more stable than two isolated alkenes. So how can we explain the stability of 1,3-butadiene with molecular orbital theory? As we said, it is not what we predicted, where there are just two degenerate pi and pi star orbitals. And this is because all four adjacent atoms of 1,3-butadiene have p-orbitals overlapping to form pi bonds. All four of these orbitals are actually aligned, and all four of these orbitals can overlap. Four orbitals overlap to form four new pi orbitals. The lowest energy of these orbitals is called psi naught, where the four p orbitals, those four atoms of this conjugated, connected pi system, overlap all in phase. So when they overlap all in phase, they form an orbital with no nodes. The next lowest energy orbital formed by all four of the p orbitals on these four atoms of butyl-1,3-diene overlap with one node. That one node is in between atoms 2 and 3. Okay, so the lowest energy orbital has no nodes. The next lowest energy orbital has one node. Recall that the number of nodes is correlated with the energies of the orbitals. The more nodes, the higher energy. We can see that phase is changing across the node, right? There will be destructive overlap here. These orbitals would be overlapping out of phase and canceling each other out. The next highest energy orbital is called psi 2. So the naught, the 1, the 2, this is coming from the number of nodes. So by my convention here, the label for the orbital corresponds to the number of nodes. So side two nodes, those nodes will be symmetrically distributed. There will the two nodes be. Just to make a note, I am arbitrarily setting the phase of that first p orbital, and then I am changing the phases of the orbitals across the nodes because that's what happens across the node. But I could have just as easily drawn that orbital like this, or I set the phase of the first orbital, this one, reversed to what I chose to do. So how I'm setting the phase of the first orbital is completely arbitrary. and then I'm just changing it across the nodes. And then finally, the highest energy pi molecular orbital made from these 4 p orbitals will have 3 nodes. So there is a node between every adjacent p orbital, and we'll call that psi 3. The difference in energy between each pair of orbitals should be about the same. My drawing is not perfect, but it should be about the same. We see that 2 of the orbitals are lower energy than the starting p orbital. Those are bonding orbitals. And 2 of the orbitals are higher energy than the starting p orbital, right? They're above this dotted line that represents the energy of the isolated atomic orbitals. And thus, they are anti-bonding orbitals. If we take a look up at butyl-1,3-diene, we see that there are 4 electrons in pi bonds. 2, 4. Like all electrons, those electrons will populate the lowest energy orbitals. And believe it or not, we have now shown why 1,3-butadiene is clearly not just 2 separate alkenes next to each other. We can see that overall, the 4 electrons in the 2 lowest energy pi molecular orbitals, which are multi-center orbitals, those orbitals are spread out over all 4 atoms of the pi system. The atoms that have p orbitals overlapping to form these pi molecular orbitals. Overall, these 4 electrons are lower energy in these 2 pi molecular orbitals than they would be in 2 just plain old isolated pi orbitals. This is amazing. And once again, molecular orbital theory has come to the rescue to explain these phenomena that we cannot explain with a different model. All right, everyone, we need to stop because very few of you probably 100% understand what I just said by listening to it one time. Okay, so we're all going to stop. Me too. I'm going to go take a break, drink some water. We're all going to stop. You are now going to revisit the molecular orbital diagram that you drew for 1,3-butadiene at the beginning of the video. You're going to modify it to reflect the conjugation in these p orbitals, right? And by the conjugation, I mean the fact that all 4 p orbitals overlap to form pi orbitals involving all of the atoms, not just the 2 atoms that appear to be making pi bonds in the Lewis structure. We know Lewis structures are imperfect. So stop, revise what you drew, write down what you now understand about conjugation of p orbitals and multi-centered pi orbitals, multi-centered molecular orbitals, and write down how those clues 1 through 3, can be explained by the MO diagram. Okay, stop, do this. It's very important for your learning. You all follow directions, right? Let's restate here that when 2 double bonds are on adjacent carbons, so there's a double bond on carbons 1 and 2, then on the adjacent carbon, carbon 3, there is another double bond. So that's what I mean by adjacent carbons. Those double bonds are said to be conjugated. So by conjugated, we mean connected, related to one another in the same pi system. Let's draw some examples of conjugated dienes and think about why these dienes are often referred to as 1,3-dienes. Well, to be connected, if one alkene starts on carbon 1, it spans to carbon 2. The adjacent carbon is carbon 3, so the 2 alkenes start on carbons 1 and 3. Okay, we can draw all kinds of examples here of 1,3-dienes, so conjugated dienes. So again, conjugated means connected. As we have observed, conjugation, connectedness of pi bonds will lead to lower energy molecular orbitals. Lower energy molecular orbitals will contain lower energy electrons. The universe is happy. Now that we are aware of these multi-centered pi molecular orbitals, for the 1,3 diene, there was the orbitals that contain the pi electrons, these 4 electrons. They are in orbitals made up from p orbitals that span all 4 atoms. That's where this term multi-centered comes from, all 4 atoms. So those 4 atoms make up a pi system. So instead of referring to pi bonds, you will hear me refer to pi systems. In fact, I've probably been doing that all semester, maybe even all year. And we didn't think much of it, but it's because it's not as simple as just a pi bond. This pi bond might be adjacent to another pi bond, and then it's going to be a pi system. So anytime there's a pi bond or a p orbital, we're always thinking in terms of, hey, well, there might be more atoms involved. This might be a pi system. So a pi system may be comprised of just 2 p orbitals. You'll even hear me call ethylene a pi system. And those two p orbitals are adjacent and aligned, and thus they can overlap and form a pi bond. Or that pi system may consist of 3, 4, 5, 6, etc. p orbitals that are adjacent and aligned, right? Adjacent means on consecutive carbons. Aligned means that they are parallel with one another so that they can overlap and form orbitals of pi symmetry. Recalling that pi symmetry means electron density above the bond axis and below the bond axis, but a node on the internuclear axis. These orbitals are formed using the same rules that we have been applying for molecular orbital theory. First, the total number of orbitals is conserved. 4 atoms with p orbitals combining in a pi system will generate 4 pi molecular orbitals, just as we saw for butyl 1,3 diene. 4 p orbitals, 4 pi orbitals. Those orbitals can combine in phase or out of phase, and both possibilities occur. When orbitals combine in phase, they overlap, as we saw in psi naught. When orbitals combine out of phase, a node is formed, as we saw in all the other pi symmetry orbitals for butyl 1,3 diene. The lowest energy orbitals will have no nodes, and then 1 node, and then 2 nodes, and 3 nodes, etc. Fewer nodes results in a lower energy orbital. When we put the nodes in the orbitals, they are symmetrically distributed. We can do this. Write those things down on your list and then move on. But wait, how can clues 1 through 3 be explained with this molecular orbital diagram? With this understanding that overall the 4 electrons in butyl 1,3 diene are lower energy in psi 1 and psi naught, and these multi-centered pi molecular orbitals than they would be in 2 isolated pi symmetry orbitals. We'll go back to clue number 1. We can finally explain why cyclohexyl 1,3 diene is lower energy than cyclohexyl 1,4 diene. Because in the 1,3 diene, the pi electrons occupy these lower energy multi-centered pi molecular orbitals. They're in psi naught and psi 1 instead of just 2 normal old higher energy overall boring pi orbitals. Great, we did it. Let's move on. Okay, this is maybe slightly more complicated. Why don't you try to explain observation clue number 2 with molecular orbital theory? Now we know that the 4 pi electrons in butyl 1,3 diene occupy these multi-centered pi symmetry molecular orbitals. So take a look at psi naught here. What do we see? we see that there's a pi bonding interaction between carbons 2 and 3. So that explains why the carbon C2C3 bond is shorter than expected. It is shorter than expected because there is pi bonding or double bond character between carbons 2 and 3, as shown in psi naught. Look, carbons 2 and 3 are overlapping in phase with their p orbitals. That makes some sort of pi interaction. So yes, it is the bond between carbons 2 and 3 has mostly single bond character. Notice there's a node there in psi 1, but there's a little bit of double bond character because of the 2 electrons that are in psi naught. All right, make sure you have clue number 2, and then let's move on to clue number 3. Explaining clue number 3 will be similar to explaining clue number 1, right? Buta-1,3-diene starts out lower in energy than 2 isolated alkenes because now we know that the pi electrons in buta-1,3-diene are in the lower energy psi naught and psi 1 multi-centered pi molecular orbitals, as we've shown here. Great, good job. We've done it. We've explained how the observations can be rationalized with the molecular orbital diagram. Let's stop and practice. We will circle the pi systems in these molecules. Pi systems will consist of adjacent and aligned p orbitals. Aligned meaning parallel. Then we will determine whether or not each system is made of conjugated pi bonds. So conjugated means connected, so really meaning more than 2 atoms. Then we will count the number of pi electrons in each of these systems. Please pause and complete this practice problem. Molecules. We're looking for atoms that are adjacent to one another that have p orbitals that will be aligned. So you can look for sp2 carbons if you like. sp2 hybridized atoms might be making pi bonds with their leftover p orbitals. They might be doing other stuff too, which we'll talk about in just a minute. But we can look for adjacent pi bonds or adjacent sp2 hybridized carbons. So in this first molecule, which is called styrene, there are 8 p orbitals, counting those 8 highlighted atoms, 8 p orbitals in the conjugated pi system, and 2, 4, 6, 8 electrons in that system. We could draw out what this conjugated pi system looks like. So each of those 8 atoms has a p orbital. As long as all of those atoms occupy the same plane, then those p orbitals will be aligned and overlapping to form an 8-centered conjugated pi system. We'll take a look at this molecule next. This molecule has 2 distinct isolated pi systems. There's the ring, and there's this double bond. This sp3 hybridized carbon in between breaks up those 2 pi systems. sp3 carbons do not have p orbitals. The s atomic orbital and all 3 2p orbitals have been used to make the hybrid orbitals. No leftover p, then no pi bonding. So there are 2 isolated pi systems in this second molecule. Now I can guarantee you if there's any opportunity for isomerization to occur, for this molecule to react in order to form a conjugated system, it certainly will. Because conjugated systems are lower energy than isolated systems. That's what we've learned today. Okay, so there's a 6 atom, 1, 2, 3, 4, 5, 6. 6 electron, 2, 4, 6 pi system. There's a 2 atom, 2 pi electron system as well. Next example, this molecule here, 1,3-cyclopentadiene or cyclopenta 1,3-diene, however you like to name it. Those 4 atoms are involved in a conjugated pi system. Each adjacent atom is sp2 hybridized with a p orbital that can align and overlap as long as all 4 of these atoms are coplanar. That system is interrupted by this sp3 hybridized atom, carbon number 5. That pi system is made up of 4 adjacent p orbitals, so it is a 4 p orbital system or 4 atom system with 4 pi electrons. We're counting the electrons in the double bonds. Are you getting the hang of it? Let's look at the last 2 examples. So for this example here, there are 2 isolated pi systems. Here they are. There's a bunch of sp3 hybridized carbons in between the 2 pi systems, isolating them. There are 2 p orbitals or 2 atoms, 2 pi electrons. And finally, this last example contains what's called an alene functional group. An alene consists of 1 carbon atom making 2 separate pi bonding interactions. So there is this pi system and there is this pi system. These 2 pi interactions are perpendicular to one another, right? How would that central carbon atom make 2 pi bonds that are parallel? It can't. It only has the p orbitals it has, and those are at a 90-degree angle. So those 2 pi bonding interactions are actually distinct from one another. They are not conjugated. And that central carbon is actually sp hybridized. So there's 1 2 atom, 2 pi electron system, and another 2 atom, 2 pi electron system. Okay, this represents one of our learning goals today, so please be sure that you can identify conjugated pi systems, count the number of atoms, and the number of pi electrons that make up each system. Once you can do that, you are ready to move on. Conformational analysis of 1,3-butadiene provides additional evidence of how low energy conjugation is relative to isolation of the 2 pi bonds. In fact, conformational analysis of rotation around what looks like the single bond, so as we've discussed in the conventional skeletal structure from valence bond theory of 1,3-butadiene, the carbon 2,3 bond looks like a single bond. We've discussed that because of psi 1, we know that there is a little bit of, psi naught, we know that there is a little bit of double bond character between carbons 2 and 3. However, it's still mostly a single bond and there is relatively free rotation around this bond. However, there are 2 stable conformations, both of which are nearly planar. Well, actually, this one is planar and this one is nearly planar. First of all, why are these the only 2 lowest energy conformations? And then secondly, which one is more stable and why? Let's give them names. So the conformation on the left is called the S-trans conformation, where S means that there is a trans conformation about the sigma bond. So the 2,3 bond. So these 2 alkenes have a trans conformation about carbons 2 and 3. The conformation on the right is called the S-cis conformation. Usually cis and trans refer to conformations around an alkene, around a double bond, but here cis and trans is referring to conformation around the sigma, the S, right, sigma 2,3 carbon bond.
This model represents the S-trans conformation of the diene. Rotation around this central 2,3 bond converts the S-trans to the S-cis conformation. Both the S-cis and the S-trans conformations are fully planar. These 2 conformations are the lowest energy conformations. There's no in-between, like this in-between conformation where the carbon atoms are not fully planar. This is not a low energy conformation. There are 2 low energy conformations, S-trans and S-cis, and are converted by rotation around this mostly single carbon 2, carbon 3 bond.
In fact, if we model 1,3-butadiene using molecular modeling software, what we find is that the lowest energy conformation is this S-trans conformation. We can see that central 2,3 carbon bond. We can see that the two pi bonds have this trans conformation about that central carbon-carbon bond. We can also see that this conformation is planar. All of the atoms occupy the same plane. So now the molecule is perpendicular to the plane of the screen, and now the molecule is in the plane of the screen. So that is the S-trans conformation. The S-trans conformation. Again, rotation around the carbon 2,3 single bond will yield the S-cis conformation, where the two pi bonds have this cis relationship about the carbon 2,3 bond. These are the two stable conformations, the S-cis and S-trans, of 1,3-butadiene. Now, why just these nearly planar conformations? Well, I think you've guessed it. In order for the p orbitals to be conjugated with one another, they must be parallel. And these orbitals will only be parallel when the molecule is planar. That is the same for the S-cis. Cool. So which of these molecules is more stable and why? Well, in the S-cis conformation, the hydrogens from carbons 1 and 4 are pointed towards one another, and there is a steric interaction here. So this molecule will go slightly out of plane. So carbon 1 is slightly below the plane, carbon 4 is slightly above the plane to mitigate this steric interaction between those two hydrogen atoms. So if the S-cis conformation is not fully planar, then there will not be full conjugation between these p orbitals. If there is not full conjugation between the p orbitals, then the system will not be as low energy as possible. So the S-trans conformation is a lower energy conformation of the diene. Because that S-trans conformation can adopt a fully planar, fully conjugated system of p orbitals.
In the S-cis conformation, there is an unfavorable steric interaction between these two hydrogens. In the model, it doesn't really look like it's a big deal, but the electron clouds of these two hydrogens do overlap in space. So in order to avoid overlap and repulsion of the electron clouds of these two hydrogen atoms in the S-cis conformation, this molecule slightly moves out of plane so that these two atoms, one is above the plane of the carbon atoms, one is below, and what that does is make so the four carbon atoms, their p orbitals, are no longer perfectly aligned. But these hydrogen atoms are repelling less in space, so there is some balance between lower energy from the p orbitals being fully aligned and higher energy when they are from the electron clouds of the hydrogen atoms colliding. So the S-cis conformation actually is not fully planar. It's a little bit askew, and that makes it higher energy than the S-trans.
Now that we fully understand our model system of 1,3-butadiene, we can draw the pi molecular orbitals for this system and explain observed phenomena based on conjugation and how conjugation lowers the energy of electrons. We can move on now and apply our skills to different pi systems with varying numbers of pi orbitals and electrons in those pi orbitals. So here are three different pi systems. I would like for you to draw the cartoon pi molecular orbitals for each of these systems, put the electrons in those orbitals, and identify HOMO and LUMO. Ready, set, go, but I want to point out that the first step is that skill that I said was so important. So identifying the atoms in the pi system. So how many atoms, because that's going to inform what the pi system will look like, right? There were 4 pi molecular orbitals for the butadiene because there were 4 p orbitals involved. And then, of course, the number of electrons in each system tells you how many electrons to put in. So you want to figure that out as well before you get started. All right, with that in mind, give this a shot. Well, for our first example, we really do have a boring old isolated alkene. We can handle this. We can handle writing the pi molecular orbitals for this system. Those 2 p orbitals combine to make 2 molecular orbitals. The lowest energy orbital involves those 2 p orbitals combining in phase. We call this bonding orbital. It is lower energy than the p orbital, a pi orbital. And we call the antibonding orbital, resulting from the 2 p orbitals combining out of phase with a node in between where they can destructively overlap, pi star. The 2 electrons of this system go into the pi orbital. The pi orbital is the highest energy filled or occupied molecular orbital of this alkene, and pi star is the lowest energy unoccupied molecular orbital for this molecule. Now we will look at a 4 p orbital to 4 pi electron system. 4 p orbitals combine to generate 4 pi molecular orbitals. Remember that the total number of orbitals is conserved. The lowest energy orbital will result from all 4 p orbitals combining in phase. There'll be 0 nodes in this orbital. Call this orbital psi naught. The next highest energy orbital will be formed from these 4 p orbitals combining with 1 node. Nodes are symmetrically distributed. It will be in between atoms 2 and 3 of this pi system. The next highest energy orbital, called psi 2, will consist of 2 nodes where the atoms combine out of phase between carbons 1 and 2 and 3 and 4 of this pi system. Finally, the highest energy orbital, psi 3, contains 3 nodes. There is a node between each pair of adjacent atoms. The 4 pi electrons in this system go into the 2 bonding orbitals. Bonding orbitals are lower energy than the starting atomic orbitals. The antibonding orbitals are empty. Antibonding orbitals are higher energy than the starting p atomic orbitals. Our last system contains 6 p orbitals and 6 pi electrons, 2 per double bond. These 6 p orbitals combine to generate 6 pi molecular orbitals. I will draw them over here because I didn't manage my slide very well. The lowest energy orbital, which we will call psi naught, will have 0 nodes. So all 6 p orbitals combine in phase for a bonding interaction between all of the atoms. The next lowest energy orbital will be called psi 1 with 1 node symmetrically distributed. So in the middle of the 6 atoms, so between carbons 3 and 4 of this system. Psi 2 will have 2 nodes, again symmetrically distributed, so that there will be nodes between atoms 2 and 3 and 4 and 5, so changing phase across a node. Those 3 orbitals are the bonding orbitals. They're lower energy than the starting atomic p orbitals. Psi 3, psi 4, and psi 5 represent antibonding orbitals. They are higher energy than the starting p orbital. For side 3, there are 3 nodes, again, symmetrically distributed, changing phase across every node, right? That orbitals combining out of phase is what causes the node. Side 4, 4 nodes, again, changing phase across every node. And finally, psi 5, the highest energy pi molecular orbital, contains a node between each adjacent p orbital. There are 6 pi electrons in this system. Those 6 electrons occupy the 3 lowest energy bonding orbitals. We identify the HOMO and LUMO for the 2 p-orbital system. We can identify the HOMOs and LUMOs for the other system as well. For the 4 p-orbital system, the HOMO is psi 1 and the LUMO is psi 2. For the 6 p-orbital system, psi 2 is the HOMO and psi 3 is the LUMO. It is the lowest energy empty orbital. We are ready to move on now. So we've looked at conjugated pi bonds, where we have multiple alkene functional groups connected adjacent to one another. And we've realized that if they're adjacent to one another, they form one system. Now we're going to move on to a different type of conjugated system. I would like for you to draw the Lewis structure for the allyl cation. Allyl means a double bond bonded to a CH2. This double bond CH2, this is allyl. We can make a comparison to benzyl. Benzyl is a phenyl ring bonded to CH2. So benzyl and allyl. For this question, I'd like for you to draw the allyl cation. Then I would like for you to assign the hybridization of each carbon atom and describe the bonding interaction between each pair of adjacent carbon atoms. Ready, set, go. We recognize that the allyl cation can be described by 2 resonance structures. These 2 resonance structures are equivalent to one another. In fact, we could draw a composite resonance structure that looks like this. These 2 carbon-carbon bonds between C1 and C2 and C2 and C3 are the same length. This, of course, is due to the fact that the molecule is described by these 2 equivalent resonance structures. To accommodate that fact, these 3 atoms, these 3 carbon atoms, are all sp2 hybridized. It doesn't matter to which resonance structure we refer to. Atom has a single geometry and a single hybridization. If this carbon atom is sp2 hybridized in this resonance structure, it is also sp hybridized in this resonance structure. It is sp hybridized in all ways that we discuss and describe this molecule, right? Individual resonance structures are imperfect. Molecules are described by a composite of all reasonable resonance structures. So the allyl cation actually is best represented by a 3 p-orbital conjugated pi system. If we take a look at the resonance structure on the left, I think we can easily identify that these 2 carbons have p orbitals that are making that pi bonding interaction. The carbon atom on the end, this carbon atom, we might say, oh, it has an empty p orbital. That's a carbocation. Well, that's oversimplified. Really, all 3 atoms have p orbitals that are all overlapping at the same time, best described by the composite resonance structure. And in fact, if we could observe this cation, we would observe that both carbon-carbon bonds have the same length. That's because the molecule is best described by this resonance structure, because there is a conjugated pi system. Let's try our hand at drawing the pi molecular orbital diagrams for the following systems, where there's 3 p orbitals like the allocation, 5 and 7 p orbitals. This is going to be fun. Let's give it a shot. After all, we've drawn the pi molecular orbitals already for the 2, 4, and 6 p orbital systems. So we can do it for the odd numbers as well. For a 3 p orbital system, there are 3 pi molecular orbitals. The lowest energy system will have no nodes, meaning that all 3 p orbitals combine in phase. The next lowest energy orbital will have one node. For an odd number of orbitals, this node will actually go on top of where an atom is. So that central atom, atom 2, it has no electron density in this orbital, which we'll call psi1. Now, psi0 is certainly bonding because it is lower energy than the energy of just an atomic p orbital. Psi1 has the same energy as a p orbital, so it's considered non-bonding. And then psi2, it will be higher energy than an atomic orbital, so it will be considered anti-bonding. There will be 2 nodes symmetrically distributed so that there are nodes between each adjacent atom. For 5 p orbitals combining, they will make 5 molecular orbitals. We're calling that the number of orbitals should be conserved. The lowest energy orbital results from all 5 p orbitals combining in phase. The next highest energy orbital has one node, which again is in the middle of the molecule, which in this case is on an atom. So you might keep that p orbital shown here, but the node there means there's just no coefficient on that atom. So if I leave it there, it's just really to represent the third atom in the pi system. Psi2 has 2 nodes, also on atoms. Psi3 has 3 nodes, distributed like this, where there is a node on that central atom. And Psi4 has nodes between all 5 atoms. Psi0 and Psi1 are bonding. Psi2 is non-bonding. Psi3 and Psi4 are anti-bonding. In the case of 7 p orbitals involved in a pi system, 3 of the molecular orbitals will be bonding, lower energy than the atomic orbitals. 1 of the orbitals will be non-bonding, the same energy as an atomic orbital. So there's no stabilization for electrons in that orbital. And 3 of the orbitals will be anti-bonding. They're actually destabilized or higher energy relative to the electrons in a p orbital. The lowest energy orbital, psi0, results from all 7 p orbitals combining in phase. Psi1 has a node on the central atom, atom 3, changing phase across that atom. Psi2 has 2 nodes in between atoms 2 and 3 and 5 and 6. Psi3 has nodes on atoms 2, 4, and 6, with phase changing across each node. Psi4 has nodes between atoms 1 and 2, 3 and 4, 4 and 5, and 6 and 7. Psi5 has 5 nodes between atoms 1 and 2, 2 and 3, a node on atom 4 between 5 and 6, and 6 and 7. And finally, Psi6 has nodes between every pair of adjacent atoms. That's the easiest one, right? Psi0, and then the highest energy orbital that has the nodes between all atoms. All right, we did it. Psi0 through 2, bonding. Psi3, non-bonding. The rest of them, anti-bonding. Well, given all of our hard work, Now we're able to identify the HOMOs and LUMOs for each of these molecules. So we're really only worried about the pi molecular orbitals. I mean, you might be wondering why. Well, frontier molecular orbitals are the ones that do the reacting, right? Pi is higher energy than sigma, so it's more likely to be the HOMO. And pi star is lower energy than sigma star, so it's more likely to act as a LUMO. So pi and pi star are more often frontier molecular orbitals, and that's why we can focus in on them today. All right, let's get at it. So remember our really important base skill is to identify the conjugated pi systems. Let's walk through each example. The first molecule is an example of an allyl cation. There is a pi bond adjacent to what seems to be an empty p orbital. So really, there are 3 p orbitals with 2 pi electrons in them. 3 p orbitals result in this set of molecular orbitals that we drew on this page. Since there are 2 pi electrons in these 3 p orbitals, those 2 pi electrons will occupy the lowest energy of these orbitals. That's psi naught. So psi naught is the HOMO, the highest occupied filled molecular orbital, and psi 1 is the LUMO. For our next example, there again are 3 pi orbitals. Now, for this molecule, we are perhaps tempted to say that, hey, there are 4 domains of electrons around that carbon. It's sp3. Well, no, it's not, because if it is sp2, then the electrons are conjugated or delocalized among these 3 atoms. We know that conjugation is lower energy than isolation. Thus, we know that this carbon actually is sp2 hybridized, that these electrons are actually in a p orbital, but really in these pi molecular orbitals, and delocalized about all 3 atoms, highlighted here in this representation of the molecule. So there are 3 p orbitals and 4 pi electrons. Those 4 pi electrons occupy the bonding orbital and the non-bonding orbital. The highest energy filled molecular orbital of this pi system is the non-bonding psi 1, and the lowest energy unoccupied molecular orbital is psi 2. Let's take a look now at the third example. The third example involves 4 p orbitals, 1, 2, 3, 4, and 4 pi electrons. This is this typical butadiene system that we've been discussing today. Our last example involves 2 isolated pi systems. Okay, so these are 2 separate pi systems where there's 2 pi cc's and 2 pi star cc orbitals. There are 2 degenerate highest energy occupied molecular orbitals, the pi cc, and 2 degenerate lowest energy unoccupied molecular orbitals, pi star cc. Be sure that you're comfortable with these examples before moving on to the next page. Excellent. All right, let's circle back. Let's apply what we've learned so far. Can we now explain why tomatoes are red using molecular orbital theory? Well, maybe not. Let's take a look at some systems that we've previously analyzed in this lesson. As the number of p orbitals increases, the number of conjugated p orbitals increases, we can see a number of things. We can see that the lowest energy orbital really is decreasing in energy. So where the 6p orbital system has a much lowest energy molecular orbital than the 2 pi electron system. We can also see that the difference in energy between the adjacent orbitals decreases as the number of p-orbitals involved increases. Oh goodness, what is she talking about? So this difference in energy between adjacent pi symmetry orbitals is decreasing as the number of p orbitals and then the total number of pi orbitals increases. So for lycopene, let's identify the conjugated pi system. It involves a lot of atoms. There are 22 carbon atoms involved in that pi system, thus 22 p-orbitals. And 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 pi electrons in that pi system. Wow, 22 p orbitals. Well, these p orbitals are going to be very close together in energy. What that means is that the difference in energy between the HOMO and LUMO of this molecule is going to be quite small. And in fact, it is going to correspond to visible light. Lycopene absorbs green light, corresponding to this energy in transition between the HOMO and LUMO of lycopene. We need to recall that when an organic molecule absorbs light, an electron is promoted from the HOMO to the LUMO. Thus, lycopene absorbs light in the visible spectrum and appears red. And it only appears red because its HOMO and LUMO are so close in energy, because there are so many p orbitals conjugated together. They're low energy. Remember the two trends that we saw? The more p orbitals, the lower the energy of the pi molecular orbitals, and the closer together in energy the adjacent orbitals became. These systems of highly conjugated pi bonds, like lycopene, sometimes absorb light in the visible spectrum. We began our discussion by looking at conjugated pi bonds, connected pi bonds, these 1,3 dienes. But now we know that we need to expand our thinking. When a lone pair, vacant p orbital, or radical is adjacent to a pi bond, actually, the orbital in question, the lone pair, the vacant p orbital, or the radical, is conjugated with the pi bond, and thus there's actually a multi-centered pi system. In fact, all three of these systems, the allyl cation, the allyl anion, and the allyl radical, are actually described by three orbital pi systems. The same three molecular orbitals result in each case because for each of these molecules, three p orbitals are combining, and they're going to combine to form the same three pi molecular orbitals. However, the total number of pi electrons will differ between these three species, and thus the HOMO and LUMO will differ between these three species. You might ask, well, why will a lone pair, vacant p orbital, or radical adjacent to a pi bond be conjugated with that pi bond? Well, we've shown that today. We have shown that electrons are lower energy in conjugated systems. This is really key. Electrons and the universe are moving towards lower energy. Electrons are lower energy in conjugated systems, and thus we observe conjugated systems. I know that it feels like a circular argument, but it is what it is. All right, how are we going to recognize these systems? Well, we're going to recognize them because often these systems are described by resonance structures. So it is very important that you recognize and can describe the four patterns for when a molecule is described by resonance structures. Because when a molecule is described by resonance structures, it actually involves a pi system. Keeping that in mind, consider how these descriptions from Organic Chemistry 1 are not quite sufficient to describe what is really delocalized pi-orbitals, multi-centered pi-orbitals that describe these systems. Here's the 4 patterns, so make sure that you remember them from Organic Chemistry 1 and think about how our current model is more sophisticated. Okay, so you can draw the resonance structures. Resonance structures, again, are a clue that we should be considering multi-centered pi-orbitals. Here are some more practice problems. Remembering that one of the most important skills today is the ability to count the number of p-orbitals and the number of pi electrons in a pi system. Once you've practiced, please summarize. What have you learned? What questions you still have? And how does what you learned today relate to what you have learned in previous classes? Be sure that you can achieve the learning goals. Can you identify a conjugated, connected pi system? I think you can, because I know that you can recognize when a molecule should be described by resonance structures. And that is a clue that a conjugated pi system exists and is the best way to describe a molecule. Be sure that you can count the number of electrons in a pi system. The trick for this is really drawing the resonance structures and thinking about the curved arrows. For example, for this molecule, there are 4 electrons in the conjugated pi system. Here are the resonance structures that describe this molecule. And to interconvert between these resonance structures, I would draw curved arrows like this. So these 2 curved arrows imply that there are 4 electrons involved in that pi system. You should be able to draw the pi molecular orbitals for a conjugated pi system. Remember that the number of p orbitals determines the number of pi molecular orbitals. Identify the frontier molecular orbitals for a conjugated pi system. The frontier molecular orbitals are the HOMO and LUMO. So to do this, you have to be able to count the number of electrons in a pi system and then put them in the appropriate orbitals. Similarly to the last lesson, we should describe how light affects the electrons in a pi system. In this class, we apply that to the problem of tomatoes and why they are red. So I hope you enjoyed this lesson. It is time to practice. So work these practice problems that I have shown here and as many as you possibly can.